Okay, so it is the scheduled time. Although we still have some speakers seems missing, but I want to start this session on time. And Ti-Rong, can I just hand over it to you?
Sure, no problem. Okay.
Okay, so let's start session 3.
Okay, hello everyone. So in these sections, the topic is search algorithms, and I'm Ti-Rong. I will host the sections for today. And we have 5 presentations in this section, and for each presentation, the presenter have 15 minutes to present their papers and followed with 5-minute QA. So for the audience, you can either use the chats or either use the QA on the bottom menu, or either raise your hand. Then you can ask the question at the QA time. Okay. So the first paper is solving nonograms, a constraint satisfaction approach. So it's from Abik, Aramian. So Abik, can you share your screen?
Yes. Sure.
Okay, so please start. No.
Can you see?
Oh yeah, yes, yeah. But I didn't see your video.
You can't see. Can you hear me?
Yes, I can. Yeah. Okay, I think maybe if you are ready, you can start your presentations. Yeah.
Hello?
Abik, are you there?
Yeah, can you hear me?
Yes. Can you share your screen?
Yes. Here it is.
Yeah, I'm not sure because I cannot
Right.
see your screen. Yeah.
I'm sharing my screen.
Okay. I didn't see the screen.
I guess there's a problem with it.
Is that your internet? Yeah, okay. I think there's maybe some internet problems. So, okay, maybe should we move to the second presentation first, and then
Yeah,
you can check.
do it later? Yeah, can I do it later after the first one?
Yeah. I think you can check your internet.
Yeah,
So the second one is generating difficult and found nonograms. It's from Milo. So Milo, are you there?
Yes. Can you
Can
hear
you
me?
present? Yes. Can you present it first?
Yes.
Okay. So please share your screen.
Okay, so I'm going to present to you my work that focus on generating difficult and fun nonograms for human players. So first, what is a nonograms? A nonogram is a grid-based puzzle invented in 1988 in Japan, much like Sudoku. And the goal is to fill a grid either with black or white cells in order to fulfill all the requirements that are. Can you see my mouse? Yeah. Okay.
Yeah. We can see your mouse.
Probably. So the clues are located on top and on the left of the grid. And for example, do you see the user interface of Zoom? No.
Yes, we can see your screen. Yeah.
No, but the user interface over here, do you see it?
No. Only
okay.
your dice. Yeah.
Okay, so here, for example, we want 4 consecutive white cells, and here we want 1 and 3 consecutive white cells, but these 4 cells in total must not be adjacent, otherwise the clue will be 4. And with these information, the player must fill a grid. Not all nonograms are deterministic, and for human consumption, the nonograms must be deterministic, otherwise it's not very interesting. And we are aiming to generate nonograms for humans. So first, before diving into the solver and everything, I want to explain how a human play a nonogram. So, for example, here we see this row as 10. So that means we have 1, 2, 3, 10. And here we have also 10. So all these cells must be white because they are because no matter how you fill the 10 cells, these cells are part of the filled cells. Okay, it's supposed to be a GIF, but it's not working. So here are the steps, and from that filling, we can get the next filling. So, for example, here we get this one because yeah, it's a true. So that means we can either put the 2 filled cells here or here, and then that means that all these cells are black, and so on and so on. So one thing that I think most humans do is that, for example, if we start here by filling this first one, and then we move the cursor to the left, we end here, and then we naturally look to the last cells we filled, because the focus of our attention is in this place. Same for here, so we go up this way, and we see that here is a 6 and here is a 4, so we know we can fill these two, and so on and so on. So, as you notice, almost every time there is a new move with the last near the last cell that was filled. So here is the rest of the process. And so solving a nonogram uses only 2 techniques. The first one that I mentioned when I was talking about the 10 row here is called swiping. And another one that is more complex is called edge solving. So edge solving is when these information are not enough. We can't no swipe is available anymore. And for edge solving, we try to basically we guess a specific cell, and then we try to fill the rest of the grid based on this postulate until, and the goal is to show that there is a contradiction and the specific cell that we inferred was not filled the way we inferred, and then we know that cell is filled the other way. So there is sweeping, this is that, and edge solving, which is a bit more complicated, and I'm not showing here because it takes a lot of time to explain. And no other techniques are required to solve human solvable puzzles, deterministic puzzles. And so, to measure difficulty and fun and anything else, we use a stack to simulate the attention of a human. So here is, first, we try to reproduce the behavior of a human through a solver. And this, since it only uses two techniques, the solver is relatively simple. So yeah, it starts with all rows and columns in a list. It iterates over them, and until the stack is not empty, it applies edge solving on each of them. At one point, maybe the stack will be empty, but not now. So it fills cells, and then it adds all the cells it has filled into the stack. So, and if the stack is at one point empty, then it tries the last retort option of using edge solving. But edge solving is like very hard. It's very time consuming when you solve nonogram, and it's only for the hardest nonograms. Most like maybe you know the famous franchise of nonogram Picross, and none of them use edge solving to solve the nonograms. Not a single one of them. So it's only for very, very hard. And if edge solving fails, the puzzle is rejected. Oh yeah, I mixed these two. Oops. Okay, so if edge solving fails, the puzzle is rejected, and if not, that means new cells are filled, and the stack is not empty anymore. So we repeat that, and once the grid is entire filled, this means the puzzle is solvable by a human, and through this process, we gathered all the data we need to evaluate the difficulty. So, what is the difficulty? There is many works on the difficulty of nonogram in a combinatorial perspective, but the difficulty for human is not the focus of many works. One of them defines the difficulty as the number of of swipes it requires to solve. But one problem is that if we try to maximize the difficulty of a puzzle, it gives that, which is not actually really hard. It's just very long, and like you only fill one cell at a time. So that's it. Except these big rows. Here, we define the difficulty first with we base our definition on their own. But we add also the number of deterministic guessing, donc edge solving, and also the number of time of large backtrackings. So, for example, if the stack, if a member of the stack is popped 7 times without any move being found, then it's determined that the last move required a lot of backtracking to find the next, and it adds to the difficulty. So difficulty is subjective, so there is not one definition. But what's great with our approach, which uses a solver, is that we can define whatever difficulty function, and even if a player knew what he wanted as a difficulty, he could tell the computer to generate puzzles specifically designed for him. Yeah. So we can keep track of other metrics. If you have any idea, I'd be interested in hearing them after the presentation. Now, for fun, fun is even more subjective, honestly. I'm not sure what makes a nonogram fun. I guess what makes a nonogram unfun is being too easy. So it must have a number of black and white tiles that is balanced. Having too much of the same moves would lead to boredom, like this one only have 1 and 18 length move. So I think this one is pretty boring to solve. And yeah, if it has a lot of backtracking, it can be annoying for some players, but I'm sure some players also like to have a bit of challenge on this point. So yeah. So we came with this function, which this member takes care of the balancing. This member takes care of the variety of the moves. This member takes care of the backtracking, and this member takes care of outlawing edge solving because they are not fun. They are just for very hard nonograms, and it's not very fun to do edge solving. So now we have these 2 functions, and we can use them in optimization process to generate nonograms. So the generation process here uses rectangles, and by combining rectangles on the overlapping areas, the values of the 1-bit vector image is swapped. Like this become 1 when there is 1 rectangle, and it become 0 when there is 0 or 2 or 4 rectangles. This helps a lot because if we selected 1 or 2, 0 or 1 for each of these cells, since the size of a nonogram is usually 15 by 15, that will make a search tree of depth 200 and something. So this is necessary to generate nonograms, but you see here on the right, it can produce slightly complex shapes with very few moves. So this one is interesting. But on the other hand, the search tree becomes very wide because there is not 2 moves, but for each move there is a ton of them. So here is an evaluation of the score functions. Here are a few nonograms, 15 of them, and under here you can see the values. So D for difficulty, F for fun, and T for time. The time is the time the solver took to solve the nonograms, and the main thing we can get from that is that the difficulty is quite good. The fun is, I mean, I don't even know what value I will give to the fun exactly to each of these puzzles, but it feels a bit right, but also it's extremely subjective, so there is no way to know. But one thing that is not accurate at all is the time. So it's simply because the solver has access to the computation power of a computer, and even if it thinks the same way as the human, each step of the algorithm is not proportional to the time it takes for a human to do. Yeah. So I think it's kind of satisfactory for the difficulty. The fun is not entirely wrong, and the time is not to be used to estimate the difficulty of nonograms. So now after we did that, we tried to optimize the difficulty, the fun, the difficulty in the time, the difficulty with the score function, and the fun of the nonograms. And there is a big difference between the deterministic algorithm and the Monte Carlo ones. So Monte Carlo ones and from UCT to the right are all Monte Carlo. But to simply explained, the variance is very high. So all the Monte Carlo algorithms are kind of similar, especially on the fun. For the difficulty and the time, there is a big difference, but it's in seconds. the big difference comes from simply that sometimes the algorithm finds a very difficult puzzle and spends a lot of time solving it. It's a 60-second optimization process. If it finds a 9-second or a 3 seconds puzzle, it's it's basically the same for 60 seconds. It's going to end the search process anyway. And yeah, very quickly we can generate fun nonograms. We can also generate very difficult nonograms because here we have the difficulty. And on the previous slide, you can see that the highest difficulty is 132. So yeah, if we try to simply maximize the difficulty, the puzzles can be very easily made extremely hard and not really fun, not really fit for consumption. And yeah, the fun is not the fun is not bad. It manages to get the highest value, higher values than any of these puzzles. So yeah, what is shown here is that we can generate difficult and fun nonograms in seconds, and that could be used, for example, if there was a time attack game mode in a nonogram puzzle, if it was ever made, this could be used that way, or maybe a generator that asks the player how difficult he wants a nonogram. So yeah, here are the main points of this research is that with a solver we can provide tailored functions to evaluate difficulty and fun that can be modified as you see fit. And yeah, estimating fun is very subjective. And then yeah, it works well. Do you?
Okay.
Do you have any question?
Okay, thank you for your presentation. Yeah, I saw some questions in the QA. The question is that, have you thought about incorporating symmetry into the fun function? My reasoning is that while puzzles may appear complex, they might not be as enjoyable if they involve repeating the same implementation on the opposite side of the grid.
Okay, so the first question is interesting because yeah, it's true that the symmetry can be unfun, but also sometimes only the symmetry can infer some like some puzzles require you to think about the symmetry to solve them. So it's kind of a simpler edge solving. Ultimately, if a puzzle is symmetric, that means it has either on the rows or the columns, it has to have repeating values, and that should mean that the variety of moves which is in the score function, the variety of moves will be lower than another puzzle, and it's taken into account. But yes, it may be a good idea to add symmetry to the fun function.
Okay.
Next week.
Another question is that, have you considered introducing colors as a new variable? For example, creating pre-cross puzzle with different colors could be an interesting extension of your solver.
Honestly, I've booked the Picross games, but I never could get into the color Picross. I just I just play the normal Picross and maybe the bigger ones that come. But the color Picross, I just I have a hard time with color Picross, so I did not think of that. But yes, maybe but I have not thought about it because I prefer black and white picross.
Okay, thank you for your
Yeah.
thank you for your answering. I think due to the time limit, we will end here for this presentation. Yeah, that's thanks for Milo. Yeah.
Thank you.
Okay, so next, let me check. Abik, are you there?
Yes, I'm here.
Okay, okay. Could you share your screen?
Okay, yeah.
Okay.
Can you give permission for sharing my video also?
Yes, yeah, I think this time works perfectly. Okay, so please start your presentation. Please also focus the time. I think there's a timer. Please try to focus using only 15 minutes for your presentation. That's we have more time for QA for all audience. Okay.
Okay, sure. Okay. So hello everyone. My name is Abik. I'm from the American University of Armenia. My supervisor is Varduhi Yeghiazaryan, and today we're going to talk about solving nonograms using a constraint satisfaction approach. So first of all, what is a nonogram? Nonogram is a Japanese puzzle game where initially you are given a top panel with some clues, a left panel with some clues, and an empty cell. So in order to solve the puzzle, you have some clues which are the keys for this puzzle. And this hidden image is the goal for the puzzle. And the size is m by n, and usually it is in a square. So here we can see that we have many clues. And if you focus on the first column, we see that we have a single clue with a value 3. That means on the first column, we have 3 consecutive black cells. On the first row, we have 2 clues, 1 and 1. That means on the first row, we have 2 black cells separate with at least 1 blank cell or a white cell. And in order to solve the puzzle, we need to somehow find some guarantee black cells. For example, if we take a look at the second row, we have a clue with a value 12. And we know that the length of the row, which is m, equal to 12. That means the entire row is going to be black. And how we solve the puzzle? We solve it using constraint satisfaction problem, which is a CSP. So in order to define a problem as a CSP, we need to find out the components of the CSP, which is the variables of our problem, the domain of each variable, and the constraints of these variables. So here we have 2 different types of CSP that makes us different from other approaches where they use the same approach. Here we have the first approach, the first type, which is the row and column CSPs, where each row and each column is a separate CSP. So in total, we have n plus m CSPs. And the second type is the nonogram CSP, where the entire board is a single CSP, so the size is 1. And now let's talk about the first type, which is the row and column CSP. Here we see that in this example, we have 12 rows and 12 columns. That means in total, we have 24 CSPs. The variables are the starting positions of these clues on each row and each column. The domain are all potential starting position of these variables, and the constraints enforce the following. The starting position of a variable plus the clue value must be smaller than the starting position of the next clue, adjacent clue, or adjacent variable. And now let's examine the fourth row CSP to understand it better. So here on the fourth row CSP, we have 3 clues. That means we have 3 variables, where each clue is a variable. And the domain of these variables are the following. This is the domain of the first variable, domain of the second variable, and the domain of the third variable. Here we see that, for example, in domain number 2, we start at index 2 because we need to let enough space for the first variable as well. So we need to fit all of them inside the grid. And the constraints. So the total number of constraints is equal to the number of variables minus 1, because each pair of variables have their own constraint. So here we have 3 variables. That means we have 2 constraints. Constraints for the first 2 variables and the constraints for the second and third variable. Here, let's take an example, this random row variable. here we see that the first constraint enforces the following: 3, which is the starting position of the first variable since we start at index 3, plus the clue value must be smaller than 5, which is the starting position of the second variable. And similarly here, the second constraint is satisfied as well, because 5, which is the starting position of the second variable, plus 4 is smaller than 12, which is the starting position of the last variable. And in order to generate the solutions of these variables or domains, we take the domain of each variable and we take the first solution or the first value from each domain, and then we merge them together and we generate a solution, which is the solution, the first solution of the fourth row CSP. And then we shift right the last black cells. And here we generate another solution and we repeat this process until we reach the end. Then we backtrack here to domain number 2. And we shift right and we repeat the entire process until we reach the end once again. And now here in this scenario, we reach the end in domain number 3 and domain number 2. So we backtrack to domain number 1 and we shift right and we repeat the entire process until we reach the end once again. So here we reach the end in all of the domains. So we stop the iteration here, the process, and this is the last valid solution of the fourth row CSP. And the second type is the nonogram CSP. Here, the variables are the rows and the columns. The domain are all possible solutions of the row column CSPs. And the constraints enforce the following: an intersection between a row and column variable must have the same color. And now let's take an example again. Here in this board, we have 12 variables and 12 we have 24 variables in total because we have 12 rows and 12 columns. And the size is n plus m. And the domain of this variable, which is the fourth row variable, is the following. So here we see that the solutions of the row column CSP that we generated previously becomes the domain of the variables in the nonogram CSP. So in this way, they are linked with each other. And also the constraints. So here, we have m rows and columns, and we said that each row intersects with m columns and each column intersects with n rows. So in total, we have n times m constraints. So each white cell is a constraint here. And let's take an example, these two random row and column variables. Here is a solution, a random solution of these first two rows, and this is another solution for the first two columns. And here we see the following. Constraint 1,1 and constraint 1,2, they are not satisfied because the intersection colors are not the same. So we need to change the value inside the domain in order to continue. Here also we have 2 rows, 2 variables, 2 rows and 2 columns. So in total we have 4 constraints. So in order to optimize the memory, we use a bit masking approach. So here each white cell represents 0 and each black cell represents a 1. For example, this random row variable is equivalent to this binary code where each one is a black cell and each 0 is a white cell. And we save it inside an array of integers. And this array of integer contains one value only, which is 21. And this 21 represents this binary code, and this binary code represents the row. And here we need only one value because each integer is 32 bits in Java. So if we have 32 cells or less, we use only one value. And let's take another scenario where we have more than 32 cells. So in this scenario, we have 33 cells. So that means we need 2 values now. The first value, the red one, represents the first 32 cells, and the last value, which is 1, the blue one, represents the last cell. And this is the worst case scenario because for only one cell, we consumed another integer value and we didn't use the 31 remaining bits. And now let's compare if we use a Boolean instead of bit masking. So the Booleans consumes 8 bits per cell in Java, but in the bit masking approach, we consume 1 bit per cell. And here we see the difference between the memory consumption per cell between the bit masking approach and the Boolean approach. And now let's do some inference. After we generated all possible solutions, we do some inference now. Here, let's take an example, the second column variable. So here we know that these are the solutions of this, the domain values of this column variable, and we do a conjunction and. By doing this, we get 4 guaranteed black cells because in each domain, the middle 4 cells are always black. And we repeat this process on every row and every column, so we get 2 grids. The left one represents guaranteed black cells coming from the columns, and the right grid represents guaranteed black cells coming from the rows. And now let's filter some domain. So let's take an example now of the 5th row variable. Here, we know that the 2nd and the 4th cells must be black. So we iterate over the domain of this variable and we remove the last one only because in the last one it says the 2nd cell is white, but we know that for sure it's black. So we keep the first 2 and we remove the last one. And we take these 2 remaining solutions of the domain or the values of the domain, and we do a disjunction OR. By doing a disjunction OR this time, we get a guaranteed white cell because in both representation, the last cell is white. And we do a conjunction and the middle cell now is black. So we add it inside the board. So now we added 2 more information inside the grid, which is the 3rd column is affected and the 6th column is affected as well. So now do we filter the domain of these columns. So now we know that the last cell is white, so we iterate over the domain of the last column variable and we keep only the first 3 and we remove the last 2 because in the values they are black, but we know that they are white. Similarly here, for the 3rd column, we iterate over the domain and we remove the first 3 and we keep only the last 2 based on the guarantee black cell. So if the nonogram has only one unique solution and it can be solved without guessing, we can solve it using inference only. But in some cases, there are multiple solutions for a single board. For example, if for this nonogram, we have 2 solutions, and if you do an inference, we stuck here. We can get only 4 guaranteed black cells, and we can't continue any further to get some information about the board. So in these cases, we do backtracking. So in the backtracking, we pick the first row, and we pick a value from the domain of this variable. And let's say we pick the first one. And then we take the first column variable. And these are the domain of the first column variable. So now, since we already picked one row, that means we need to find a value from the domain that matches that single black cell. So we do a binary search now here twice inside the domain to find out the best values that agree with that black cell. So since here we have only one valid solution, so both binary search stops on the first value. So we pick that value now. And let's assume now here we picked already 3 rows and we picked already 2 columns. So now is the turn to pick a value for the 3rd column variable. So this is the solutions or the values of the domain of the 3rd column variable. And we already picked 3 rows. So that means this column intersects with 3 rows and they are all white. So now we do a binary search. So this is the first valid solution and this is the last valid solution. So we pick the first one, and in case of backtracking, we pick a value from this range. So this is some comparison with a survey of paid by number puzzle solvers. So here we can see that we have some different solvers. Here we solved 2,491 puzzles with different time slots, and the last 2, our sequential and our parallel, our approaches. Our sequential means that we used a single process, but in our parallel, we used multiple processes in order to solve the puzzle. And we are from the top 2 in this table. Also, some future work, we want to solve the nonograms with the multiple colors. So here, there are some challenges because we can't use a binary representation because in the binary representation, we have only 1 and 0, but here we may have multiple colors. And thank you, and I'm open for any questions.
Okay, thank you for Abik's presentation. Are there any audience have questions? Okay, so let me ask one question. So you mentioned that in your approach, there might be some puzzles have multiple solutions. Yeah. Yes. So how do you deal with that situation?
So if you have multiple solutions, in that case, our inference will fail. And after that stage, backtracking, which is the most straightforward approach. for solving.
Okay.
Backtrack.
So
Yes.
So just try every possible from the beginning.
Combinations until we solve the puzzle. But in our comparisons, we only compared work with some other puzzles where the puzzles are unique and can be solved without guessing.
Okay, I see. Okay, are there any more questions? Okay, we have one question from the audience in the QA from friend coast. What are roughly the maximum size that you can solve with your solver? How does it scale with the size?
Yes, that's a good question because we had a big nanograms, for example, like 80 over 80, 80 rows, 80 columns, and we couldn't solve them because our memory got full. So the maximum size, I can say it's 60 by 60 as far as I've seen in my experiments. Because we generate a lot of solutions, so for that reason, our heap memory gets full, so we can't continue.
Okay. Are there any more questions?
I see Milo is raising his hand.
Oh, okay. How should I turn? Milo, you can just turn on your microphone and ask.
Hello. From the dataset of nonogram puzzle you used of few thousand puzzle, do you know if there are any nonograms that is not solvable using only swipes and edge solving?
No, I'm not familiar with that.
Okay, thank you.
Okay, if anyone want to ask a question, you can either raise your hand or type your question in the QA or chats. Okay, we have one more question from the audience. The question is, you said it was memory limitation. How much did you use during your testing? How additional memory would increase the limit?
Yes, in my experiment, I used 8 GB heap size. And I guess if I increase it, and if I have a more powerful computer, I can solve more complex puzzles with higher dimension.
Okay, if there's no more question, maybe we will end this presentation here. Okay, that's thanks for Abik again. Yeah.
Thank you all. Goodbye.
Okay, so the third presentation is from Tristan. The title is Monte Carlo Search Algorithms Discovering Monte Carlo Tree Search Exploration Terms. Yeah. So Tristan, are you there?
Yeah, do you hear me?
Yes. Could you please share your screens?
Do you see my screen?
Yes. Okay. So please start whenever you are ready.
Okay, so my talk is about using Monte Carlo search to improve Monte Carlo tree search. So there are multiple ways to do this kind of thing. So what I do in this work is to find a new exploration term for Monte Carlo tree search. So here is the outline of my talk. I will first give a broad view of algorithm discovery using Monte Carlo tree search and deep reinforcement learning. And then I will talk about discovery of Monte Carlo tree search algorithm, not only different algorithms and in algorithm discovery. So the discovery of MCTS algorithm with other algorithm. And then I will explain the contribution of the paper, which is discovery of Hsueh's exploration term. So first, algorithm discovery. So algorithm discovery is using algorithm to generate new algorithms that have good properties. So we use an algorithm to discover an algorithm, and people from DeepMind, they use the AlphaZero and Mu0 to play this game of finding a new algorithm. So they had quite some success with this approach. So in 2022, so this is a cover of Nature in 2022. So they used Mu0, so they use Monte Carlo tree search and deep reinforcement learning to discover a new fast matrix multiplication algorithm. So to do that, they represent the matrix multiplication algorithm as a tensor, and the goal of the algorithm discovery algorithm is to find a tensor that represent an algorithm that is fast for matrix multiplication. So they found again the standard matrix multiplication algorithms that are better than the naive one, and they also found a new matrix multiplication algorithms that were faster for some cases of some matrix sizes. So this is a use of Monte Carlo tree search and deep reinforcement learning for finding algorithms that are different from Monte Carlo tree search, that are general algorithms. The year after, they published AlphaDev, which is also using the same kind of thing. So playing the game of algorithm discovery to find a sorting algorithm. And they found a faster sorting algorithm using this approach. And last, they used AlphaTensor, so the program that does algorithm discovery, to do quantum circuit optimization this year. And this was also an achievement by automatically finding a good circuit in quantum computing. And other people from Google, so Coakley team, they used automatic algorithm discovery with a symbolic search to find optimization algorithm. So the algorithm the algorithm that the algorithm found is called Lion, and it was compared to Adam, and it has better memory consumption than Adam, so it is slightly better than Adam, and they used it to train some neural network efficiently. So as you see, there are many applications of automatic discovery of algorithm. And what we are interested in this talk is discovery of Monte Carlo tree search algorithm. So I first started to work on automatic discovery of Monte Carlo tree search algorithm in 2007. So at that time, I was using genetic programming to invent a new exploration term for Monte Carlo tree search, and it had found some exploration term with all move as first heuristic that were better than the usual UCT at that time. So it was in 2007, so I was using genetic programming. In 2010, I used nested Monte Carlo search, so Monte Carlo search that used Monte Carlo search to discover mathematical expressions. So this was as a comparison to genetic programming, which is also used to discover mathematical expression, and I had good result with nested Monte Carlo search for this task. And nested Monte Carlo search can be used to replace genetic programming to discover new Monte Carlo search algorithm with Monte Carlo search algorithm. So it comes to what I did for this paper, which is a discovery of exploration term for the Hsueh algorithm. So Hsueh is a sequential halving using scores. It is based on the sequential halving algorithm. So sequential halving is an algorithm that minimizes the simple regret, which is a regret of not finding the best arm at the end. So here is the algorithm. So it's quite simple. it works with a number of rounds. So at the beginning, you have all possible moves that are in the set of moves to try. And what you do is that you give some play out to each of the moves. You give a budget. So the budget gives you for each move after it has been played at the beginning of a play out, the average of the reward for this move. And sequential halving, what it does is that it takes the best half of the moves that are sorted according to their reward. So it takes only the best half of the moves. And when it has done so, it gives again some play out to the best half, and then takes the best half of the best half, and continue like that until there is only one move left in the set of moves that you try, and it decides to play this move. So what we did before is to use sequential halving at the top of a PUCT search. So what we usually do, and that works well, is to use sequential halving at the root of the search tree, and to use a PUCT for the playout, so that it learns to play below the root. And this is efficient in many games. So the improvement on sequential halving that we published with Nicolas Fabiano is sequential halving using scores, so Hsueh. So the idea of sequential halving using score is to use a prior to improve the mood selection at the root. So in the Hsueh paper, we proposed two ways to do that. So the first is by using AMAF. So we add to the Q value the standard AMAF value of a move divided by the number of times the move was tried. And this improves on sequential halving by using AMAF. So another thing we propose in the Hsueh paper is to use a sequential halving with a policy network. So we have a neural network that gives probability to the moves. And the way we use the policy network with sequential halving in Hsueh is to select the n best move according to the policy, and to perform sequential halving on this set of moves. So we only try the most promising move, and we only give play out to these moves. So we have to adjust the hyperparameter, which is n, so the number of best moves that we keep, and this is dependent on the total budget that we have at the beginning. So we applied this in this paper to the game of Go, and we use a neural network that gives a policy on the value, which is a transformer trained on the Katagao games. So in order to evaluate some expressions that we generate automatically, we modify the Hsueh algorithm. So we still keep only the best n move given by the policy to do the sequential halving, but instead of using the average of each move, we use an expression, a symbolic expression. So here it's an expression of SR of J, which is automatically generated, and we evaluate the expression by using a data set that we have generated. So what we do is that for each expression, we test it in the sequential halving algorithm. So the expression we generate are composed of atoms. So we used this set of atoms. So the possible value for a leaf are 1, 2, 3, and 100. So there are 4 possible numbers for a leaf. We use SC, which SC is the sum of the scores of the playout starting with the move. So this is the sum of the reward for the moves that we consider. And we use PR PR is the prior for the move given by the policy head, so the transformer network that gives the probability that the move is the best one. We also use NBP, which is the number of playouts starting with the move. So if we divide SC by NBP, we have the Q value. And NB, which is the total number of playouts. So we had this because in the PUCT bandit, this is used in the square root. So besides these atoms that are specific to the sequential halving algorithm, we use a general atom, which are the usual operations, so plus, minus, multiplication, division, logarithm, exponential, equality, and max and min. So the idea is that using this atom, we randomly generate some expression, so some mathematical expression, so some trees that represent an expression, a mathematical expression. And we tried an improvement on automatic generation, which is to use the AMAF value for the atom instead of uniformly generating atoms. So the way we do that is that we represent an expression with a stack of atoms. So instead of having a tree representation like in genetic programming, we represent the tree as a stack in a reverse Polish notation. And this enables to use nested Monte Carlo or sampling very easily, because you just have to push atom on the stack until the expression is complete. So we did compare sampling with AMAF statistics on the atom with sampling, with uniform sampling. And what you can see in this figure is that sampling with AMAF is better than uniform sampling, and it gets the same kind of value, the same kind of accuracy on the dataset than sampling uniform, which is 8 times slower. So yes, I did not tell you about the dataset. So we did generate the Hsueh dataset. So the Hsueh dataset is a dataset where we took a random state from the Katago self-play games. And for each of these states from Katago, we use Hsueh with sequential halving with 128 evaluations, the standard sequential halving. And the way we evaluate the expression is that we use Hsueh with the expression with 32 evaluation, and we look at the accuracy of Hsueh on the expression with 32 evaluation on the data set of moves that were found by sequential halving with 128 evaluation. So here on the top, you can see different exploration terms. So for example, PR, which is the probability of the move given by the policy. If you use PR as an exploration term, then on the Hsueh dataset, you get 44% of moves that are found by Hsueh with 32 evaluation, which is not very good. So if you use the standard exploration term SC, so SC is the sum of the reward. So by taking the sum of the reward, you just do the standard Hsueh algorithm. And this time, it gets 71% of accuracy on the Hsueh dataset. And finally, there is a PR plus 2 times SC times SC, which is a discovered exploration term by our sampling algorithm. And this term is slightly better than the usual sequential halving. It gets 72% on the Hsueh dataset. So we tried different datasets. So the Hsueh dataset is the one that works well. We also try to use the Katago moves or moves given by PUCT, but this works. This doesn't work very well. What works very well for learning a Hsueh term is to use Hsueh with more evaluation. So in the bottom, you see the result of Hsueh playing against standard PUCT, so standard Monte Carlo tree search. So when you use the standard Hsueh with the SC exploration term, which is some of the reward, you play hundreds of games against PUCT. You get 42% win rate, which is not bad, but which is worse than PUCT. And if you use exploration term, which is PR plus 2 times SC times SC, you get a better result against the PUCT. So it wins 51% of its game, which is much better than the standard Hsueh. So by using this method, we were able to generate exploration term for Hsueh that is better than the standard exploration term used in sequential halving. To finish with that, we did sampling of exploration term, and we generated the Hsueh dataset for evaluated this generated exploration terms, and we found an improvement on sequential halving using this automatically found exploration term. And it makes Hsueh competitive with PUCT for small budget. So we only tried a small budget for this. Even if with more budget, it also improves. And if we analyze the exploration terms that was found, this is something that when there is only few playout, give some weight to the prior, and when there are more playouts, so the term is a PR plus 2 times SC times SC. The 2 times SC that multiplied by SC gets much important, so much bigger when we have many playout, and it behaves as the usual sequential halving. So the improvement in the exploration terms that was found was to use the prior when there are only quite a few, very few playouts. So in the end, we find a new exploration term, and so in the future work, we want to apply this kind of idea to other Monte Carlo research algorithm and to improve on the current exploration term.
Okay, thank you for Tristan for a great talk. So, does any audience have questions? Okay, let me ask one question. So, in your method, is it possible, because you can automatically find the exploration term, so is it possible to maybe combine it with the PUCT, like the parameters? Is it possible to combine together or not? Yeah.
So you mean to combine with PUCT?
Yes. Yeah.
So well. So here it is already combined with PUCT since in Hsueh we use sequential halving at the root, but below the root we use PUCT. So this is we also already use PUCT. But what would be interesting, for example, is to first discover again the PUCT term, which would be interesting. Maybe try to find some improvement to PUCT for some problem or for some games. So so clearly PUCT is a standard now, and we can hope to find something which can be slightly better than PUCT, but for the moment I did not try this yet. But it should be interesting to try to automatically improve on PUCT using this search for exploration terms.
Yeah. Okay. Yeah. And another question is that because you're using the sequential halving, I'm thinking that have you heard that the algorithms that's called Gumball Alpha Zero or Gumball Mu Zero, they also propose using sequential halving combined into the Monte Carlo tree search. So could you explain the difference between this approach and the Gumball approach?
Which approach?
Your approach, and do you know the Gumball Alpha Zero or Gumball Mu Zero?
Yeah, so yes, so Gumball Alpha Zero and Gumball Mu Zero, yes, they use also sequential halving. So this was posterior to our work with Nicola Fabiano on Hsueh. So they use the same kind of things, yes. And well, so I did not compare the exploration term we use with Gumball Alpha Zero or Gumball Mu Zero. But they use the same kind of idea, so they use sequential halving in order to minimize the simple regret, and this is efficient. So yes, that would be a nice idea to try this approach of automatic discovery on Gumball Mu Zero, which has some success.
Okay, if there's no any other question, let's thanks for Tristan for this talk. Yeah. Okay, thank you. So next presentation is from Wei-Lin. The title is Zweistein, a dynamic programming evaluation function for Einstein Würfelt Nicht. So Wei-Lin, are you there?
Yeah, I'm here.
Okay, could you please share your screen and open your camera?
Sure. Why? Let me rejoin. Maybe I can turn on the camera.
Okay. Okay, so
I still can't able to turn on my camera.
Okay, maybe just share your screen and start the presentation. Yeah.
Okay, sorry for this technical issue.
Okay, so please start when you're ready.
And hello everyone, my name is Wei-Lin Hsueh, and I'm going to present this Zweistein. It's a dynamic programming evaluation function for Einstein Würfelt Nicht. And my supervisor is Tsan-Sheng Xu. Let me do a brief introduction of this Zweistein function. And it's the winner in the TCGA 2023 computer tournament in Einstein Würfelt Nicht. And the abbreviation is called EWN. And the name Zweistein is a pet phrase from my German teacher, so it means twice as smart as Einstein. So it should be pronounced in German, just like the Einstein Würfelt Nicht. Let's start introducing the rules of the game. So initially, there are 12 pieces, and there are red and blue, and each player, and the numbers ranges from 1 to 6. And initially, red players are on the top left corner, and the blue players are at the bottom right corner. And I will explain the game procedure here. At the start of the turn, players first throw a dice. And the movable piece will be decided by this dice number. And for this example, the dice number is 4. And let's take a look at the first example. The alive number for the red player is 1, 3, 4, and 6. And you can see there's a match to the number and the dice number. So you can only move number 4. And the second example is that there are no piece 4 exist. Then in this case, we have to search right and left. So you can move either 2 or 6. And after you're choosing a piece to move, then you can choose a moving direction afterwards. For red pieces, you can move in these 3 directions. And for blue pieces, you can move in these 3 directions. And there's a special rule called piece capturing. If there is another piece located at the destination, it will be captured, and no matter the color it is, you can capture your teammate or enemy. And there are 2 kinds of winning conditions. The first one is reach the corner. If one of the red piece reaches the red corner, red wins. Or if one of the blue piece reaches the blue corner, the blue side wins. And another condition is called capture all. It happens when red pieces capture all blue pieces. And in this case, red wins. And when blue pieces capture all red pieces, blue wins. Then we can talk about some common ways to design an evaluation function for this game. And the most common way is to manually tune some parameters to combine several factors we concerned. And here are 2 examples here. The first one is ODEMA, and the second one is EWNY. You can see that they both combine some multiple factors with some parameters. And the third related work is called Schwarz table, and it's designed by Stefan Schwarz. He simplifies the game by disabling the piece capturing, and he calculated the expected remaining steps as heuristics. And let's talk about the core of these Zweistein functions. Zweistein has no parameters, unlike the above examples, so there's no need for any tuning. And the core of Zweistein is to strongly solve a simplified EWN. And the only difference with the original Einstein Würfelt Nicht is the piece capturing rule is removed, just like Schwarz table. And how to solve this simplified game? First, we can convert the position to a vector of Chebyshev distance. Because piece capturing is removed, so the position is not very important. And the thing only matters is the distance. And you can see the size, the number of unique boards decreases from a huge number to 15,625 for one side. But if you want to strongly solve this game, you need to consider both sides. And all possible boards for this is 5 to the power of 12. It's about 244 million. But the method in our paper, we managed to solve this game with a much smaller size. How we achieve this is because piece capturing rule is removed. So the only winning condition is to arrive the corner. Then the win rate of this game suddenly becomes the probability of arriving the corner earlier than the opponent. And if you write it in a formal mathematic notation, it's like this: probability x smaller than y, and x is the random variable of the remaining steps for our side, and y is the same variable but for the opponent. But you cannot directly calculate this. This is not a straightforward computation task. So we need to split this value into a summation form. So we need to enumerate all possible remaining steps, then calculate and sum the probabilities one by one. And the 19 is the maximum value of the remaining steps. It comes from a worst case scenario, assuming all 6 pieces have the distance of 4. And in the worst case scenario, all of them cannot reach the goal. So all of them just go to the distance 1 positions, which cost 18 steps. And you need 1 last step to reach the goal. So it's 19 steps. And if you look at this summation form, you can see that calculating this win rate requires only a cumulative density function for x and a probability density function for y. And after knowing how to construct this function, let's look at some experiment result. ODEMA is the function we talked about in the related work. And we do this experiment with each data point is the win rate of 100,000 gameplays. You can see that when the search step is greater than 1, the win rate is consistently larger than 50%. And the second function is EWNY, and it's the second place winner in 2024 TCGA. We do the same experiment, and the win rate is the same, 100,000 gameplays for each point. We can see that Zweistein cannot exceed the 50% threshold. But this doesn't mean that Zweistein is inferior to the EWNY, because when we look at the execution time, because Zweistein is very simple, so it is very fast. It is about 40% faster than EWNY. So if we if we redo the experiment, but we change the constraint from search depth to time, and to ensure the fairness, we use the same dynamic time controlling policy as below. And in this new experiment, the win rate when time limit exceeds a threshold between 4 to 5 seconds, Zweistein can outperform EWNY. And then because Zweistein is a win rate-like value, so we can compare it with the exact win rate. we use the brute force method to get the exact win rate, and it can be verified. So in this first example, the exact win rate is 0.56, and the value of Zweistein is 0.58. So the accuracy is very high because piece capturing is unlikely to happen in next few steps. So removing the piece capturing rule won't affect the win rate by a lot. Well, this is another extreme because blue players can easily avoid losing by capturing red 5. So the exact win rate is not that high. It's about 0.65. But the value of Zweistein is 0.95 because it doesn't know that blue can capture red. So it will be very optimistic about the win rate of the red player. However, a simple depth 1 search algorithm can solve this problem because piece capturing can happen when you do the tree search. So the searching algorithm can greatly lower the error and make the value way more accurate. After a depth 1 search, the value becomes 0.6, and the difference is only about 5%. So that's why Zweistein is weak in lower search depth, just like the previous experiment shows, but it becomes stronger at a higher search depth. And for the related work 3, there's another person use a similar concept to like simplify a game with removing the piece capturing rules, but he didn't solve the game. He actually calculated the expected value of remaining steps, and we can compare both methods. So let's look at the first board. It's an ensured win for the red when blue moves first. So Zweistein gives a very accurate result, 1. But Schwarz table result gives 1.53. And the second board shows that it's not a guaranteed win for the red. And Zweistein actually very precisely predict the win rate, and the error is very small. But the Schwarz table seems like it overestimated its value. So Schwarz table cannot precisely predict the win rate, and it might sometimes underestimate a very good board or overestimate a not very good board. And here are some future works that we can do. The lookup table for the Zweistein is about a few megabytes in size, and it's very, very small. So there are a lot of potential in that. If we expand the database to include some partial rules of piece capturing, then the strength of this evaluation function could be further enhanced. And my presentation ends here. And please ask questions if you have any.
Okay, thank you for Wei-Lin's presentation. So, are there any questions? Okay, let me ask one question. So, you have a comparison between your phi psi and EWNY, and you mentioned that if the thinking time increase, then your win rate can be higher. Yeah, but I'm wondering, it looks like this curve are not gradually increase. Like for example, when the time limit is 8, there's a decrease. Yeah. So are there any reason for this situation?
I don't actually do the very detailed research in that, but I have a very I can guess that it's because the search limit when the search depth increase by 1, then the time limit, how to explain it? I mean, when the time limit across a threshold, the search depth suddenly increased by 1. And this can suddenly increase the win rate for a player.
Okay, so if the time limit is larger than 10 seconds, what do you expect? The win rate will keep go higher or have the same similar situation?
I think the situation will be similar. It will go like up and down. It won't be higher continually.
Okay. Okay, we have one question from the QA. It's from Elsa. I like your observation about the game. Did you have any comparisons on different versions of Einstein playing itself? I'm curious how big the win rate difference is between original Einstein and Einstein plus depth minus one search. Depth one search, yeah.
Oh, actually, it's just adding a additional depth in the searching algorithm. I actually did some similar results from similar experiments before. When the depth is low, like you increase the depth from 2 to 3, the difference is big. But when the depth is way larger, like you increase the depth from 7 to 8, the difference is not that big anymore.
Okay, thank you for your answering. Okay, I think due to the time, I think we just end this presentation here. Yeah, thank you. Let's thank you for Wei-Lin's again.
Yeah, thank you. Thank you.
Okay, so the final presentation is from Wayne. The title is Chinese Chess EGTB with Perpetual Check-Chase Rules. So,
yep, I'm here.
Okay, so could you please share your slides?
Yeah, I start sharing. Can you see the screen?
Not yet. Oh yeah, yes. Okay, so please start whenever you are ready.
Yep. Hi all. So my name is Nguyen Pham. My presentation about the Chinese chess EGTB with the Perpetual Check-Chase Rules. It might be I prepare, so maybe I'm not sure about this. Maybe too long or too short. So I just start, and my English is not good. So I try to speak a bit slowly, and so we can understand each other. So my work mainly about three things. First is about the endgame table base, with the short term is EGTB. The second one is Chinese chess or Sankey. And the last thing is about the Perpetual Check-Chase Rules. I write the short form is PCC. So three things combine each other. We will go one by one shortly. First, endgame table base is for, it's kind of database of endgame for computer chess. Each game is they divide the EGTB by multi end games. It's about the material like the end game with rook, end game with pawn, end game rook again pawn. There are some examples about the end game table base, like the Nalimov, very famous and very first one famous, series Gaviota. About the draw by the 50 moves rule in chess, You know, in the chess have the 50 move rules is symbol when the is simply ruled by as a draw, and only one of our EGTB consider about that rule is a series. The other, on the other, include my own growth, Thompson, many one Chinese chess ignore that rule. So it means we don't care about the draw by 50 move rule. We to generate the EGTB, we use the Thompson method. It's Roucairol generation. And you see that the first step, we initiate all the position in a database by the unset value. We start from the second one, we start from the met immediately, met in zero. It means met immediately. And then we redraw, come back, find the move, the parent met. It means met in one. And then met in two, met in first we have the met win in zero. It means we have a met loss in zero. It means we have the met win in one, and then we have met loss in two, and extra until, and we do repeat until no change. And the last step, we change on the unset position by draw value. So you should notice that this one, unset position by draw value. So we see clearly a bit so deeper about the unset position. So it means unset position, it means non-progressible, unwinnable, because they you see that in the end they are draw. So unprogressible, unwinnable, unlossable. So it means they own draw, and you see that the draw there are mainly two rules about the 50 move rule. But I noted before that we don't count that rule. So it means we ignore the 50 move rules, and only it means in our database is only mean repetition, a loop. So we noted it because we will because my work based on that. Chinese chess, Sankey, so many authors apply Chinese chess to chess engine and include the database chess EGTB. So we see that Chinese chess look like that. The first picture is Chinese chess in English, and the second one is in the Chinese chess in Chinese character. I can't read Chinese, but I can still play Chinese chess with the Chinese character. So we have some terminology. So in Chinese chess we have two kind of piece. One is attacker, is rook, cannon, horse, pawn. They all can go to opposite land to attack opposite king. So they call attacker. And the other is elephant and advisor. They cannot go to opposite land. So they mainly to defend their kings. So we call defender. And one side we call armless if no attacker, and one side is arm if have at least one attacker. So, and based on that, we divide the Chinese chess endgame into three. The first one is simple, none have attackers. So it's always draw. We totally ignore that. The first one. The second one is arm side, one side arm, and the third one is two side arm. The second one, one side arm. You see the picture, the first picture here. The white have only have attacker rook. The black have king and advisor is defender. So they cannot go to attack the white. So that's one side arm. and it's shown, I mean, in the term of endgame database shown by the other author. The last one is two sidearm. You see that white have rock and the black have cannon and pawn. So this one not shown. And it's my work of it's my main work for this research. People don't chase. We will discuss here a bit. It's a rule, a Chinese chess rule. When repetition occurs in the chess, they mainly draw game at a draw. So it's very simple and quick for chess. But for Chinese chess, it might be rule the game at it's stop. When the repetition is stopped, similar to the chess, is stopped, but it's rule different. It might be rule at draw, but might be rule at loss for violent size. It means someone chase or check permanently the opposite side. So this one makes the Chinese chess very complicated and hard to implement, hard to understand and hard to implement. So we mentioned more about the people check and chase. So we see that is a repetition, and one piece of one side being attacked and then evaded consequently. It means one side set attack to that piece, and the other side try to escape it from the attack. And only that kind of piece count as the PCC. But if one side stop attacking and the other side stop escape it, evaded it, even in one move, it's not count. And after run a game, after know that a repetition is a PCC, we still have some extra condition like the king can chase, or a P might be being protected or not, or maybe it's exchanging situation. So it means it's complicated too. But the first three things is more complicated. The previous work is based on my work in the 2018. I implement the complicated rule for Sankey for Chinese chess. So I implement it based on create two pair of array of being attached, and I maintain the pair one by one, but after each move, and after each move I compare the new pair with the main pair. So I can update the location of moving piece, and I can keep only the one being attacked or evaded. So after one move, I update the pair, the attacking pair, and then I know which one is changed, is one still in the chain list, which one is not. So until the end, so I win in the last situation. Maybe the side can be to one, and then I check more condition to check it. So it's mainly it's my work of previous work, and I can use that on my work to the new one, to this current one. So I suppose that all the Chinese program like the chess guide or chess engines implement PCC rule. You know that in the past someone said that they implemented PCC rule, but after we verify that not like that, not really true. So in my case, we use my previous work and to implement it. So I have a probe function when probing. I suppose we probe like that. First, we check if there are repetition or not, or if not. If yes, we judge it by the PCC rule. Otherwise, we check if it hits at the end game and probe it. or do the normal search. So we see that the first the L here from L here is traditional way. I just add the way my way here. So I will always check again is repetition and run by PCC before everything. So I must make sure that if I do that, the game always legend. End game of one side arm. So as I say, you can see the picture here. So I just say quick because one side have no attacker, so it cannot win. So it means the attacker always have move to make. So it's never worry about the violence to the PCC rules. So the arms, the one side arm is always have legend, can play a legend game. So it means we don't need to do any special thing with the end game of one side arm, and we call it traditional way, and it can work well with the one side. And many previous authors like Pham, Reno, they read only this class to avoid implementing the PCC. Endgame of two side arm. So you see that example here, and you see here is the black can win. The black can win immediately in one move. Just move here and win, and the white cannot make the game cannot protect his king. So we see that it's try to move this to move here from this one to here to check the king, and king down, and it's down, it's follow up and down. So creates the permanent check. And you see that for traditional way, this one is repetition, so it's draw, it's kind of draw. So the similar for the chase, rook chase come here because the black winning. So because the black here is winning. So rook come to chase the rook, attack to try to attack the cannon. And when cannon come, this column is follow. So it chase the cannon to avoid being lost. And traditional way, you see that is draw position. So it means for traditional way, it's not enough, not good enough. Because this thing is repetition is no progress. So and you see that and with traditional way, very hard to solve that problem. If we buy on the data, because you see that sometimes we have to search very long, very deep to find it. This is not a win, not a draw, but a loss. So we have to search very deep. So in the my research, I try to detect this position. It's not real draw. It's PCC. It's lost because it's permanent chase. So I have to find this one. When the rock move here is position here, it's not draw. And I'm fin by the special value. And you see that we call this Perpetual scores. And it sits between the met and the draw. Met, normal evaluation, draw, it look like the chess, like the normal chess. And we fin in the middle score here by some special score. So it's recognized by the range, by the value here. So it's know that it's people check or people chase or forward. So main idea of our work is to find the position to start PCC processing. And actually we start with the unset position. trade up the unset position to find the repetition. And once we have the repetition, I use my previous work to value it, to score it. So to I make it that position is start a repetition and is maybe make a permanent a change, repetition change or permanent checks, and I find the right PCC value. So you see that then here we have the algorithm, our algorithm here, and our algorithm here. I insert in the three new steps here, and you see that actually my algorithm before the last step, and we just follow the unset value to find the repetition and then value it. If it PCC, I will win permanent check or perpetual chase. And the algorithm is quite long and hard. So I try to divide by, because I use kind of alpha beta function. So I divide by the evasion and attacks. And
hello, sorry, right, Win?
Yep.
Yeah, so it's already 80 minutes. Could you please speed
Okay,
up your note, maybe within 1 minute? Yeah.
So on it, the idea is simple, but the implement is quite hard because it is you see that create the rule more complicated. So I generate a lot of small end game to just for make sure that our work my algorithm is work. And you see that some data here, and so conclusion one side don't need to PCC. Two sides must have, and I have the algorithm and event it in on open source. And you see that I have reference, and I have the open source in the GitHub. That's on my work. Yep, I done.
Okay, thank you for Win's presentation. So yeah, I think due to the time, we welcome only one questions. Are there any questions from audience? Okay, so so maybe let me ask one question. So in your algorithm, are you trying to solve some endgame or just to improve your Chinese chess program?
It's the purpose is I generate the endgame database. EGTB, we generate a lot of here, and when we have it, we have the multi-purpose, like we study how to finish an endgame, or we can use it for improve the strength of chess engine. So my study use for knowledge, human knowledge, and for computer strength.
Okay, I see. Okay, so yeah, thank you for your answer. Okay, so I think thanks again for Win's presentation, and I think we just end here. And for this session 3, all of the 5 papers presentation are finished. So yeah, the session is end here.
Okay, thank you, Ti-Rong, for hosting this session, and also thank all the speakers for their presentation and the questions from the audience.